haven't checked in a while.
On Zoom, yeah. It's out there for, if you can't make it and you can't make Zoom, it's always on YouTube, and all of the meetings are on YouTube. So you can go back and look at all of the other meetings and see all of the other speakers, which are also all very good. Well, that's good.
Okay, it should be going to Zoom. Evan, can you check it?
I am checking now.
I think I have to stand here to be seen.
Yep, I can see it Zoom. Yep.
Okay, great. Thank you. All right.
We
are ready. We're good to go.
Okay. So
you
we
want
have
the
a new
agenda up
member.
again?
Sure, you can put the agenda up again. We have a new member here. I'm going to hand him the microphone. Here you go.
Hello, my name is Patrick Schuss from Redondo Beach. I joined in June, and I found you by looking for astronomy groups in Los Angeles. So LAAS came up, and I've got two friends, Brian and Norm, and we're doing astronomy and having fun.
Thank you for coming. Anybody else? Just the one for tonight? Okay, that's fine. Any new members on Zoom? I hear no yeses. All right. Well, then, so the Star Party on the 13th is also the new member potluck. No, that's on the 20th. Okay, so the 13th is the Griffith Observatory Star Party, which is going to be here. Please come. LAAS new member potluck and swap meet is on the 20th. That is at Garvey Ranch. That should be also really good. And family night on Lockwood, Dark Sky on the 27th. And well, you think I can read it there, but it's not that. It's harder to read over there than it is over there. I understand. That's okay. They can look at the back. Let's see. So what else do we have? The August meeting. The August general meeting here is going to be at the planetarium. I believe Dave is going to be back, or he is back, and he's going to be doing a planetarium show that night. So we will not be here. Yeah, I think he's back. He's on Zoom. Okay, good. Oh, that's why I saw his name. Anyway, Dave, thanks for getting well enough to come back and do our.
You're welcome.
Our meeting on August. So, if for whatever reason that gets canceled, there won't be a night because we're not going to be here. It would be just a Zoom-only meeting if that happens. Other than that, anybody have any questions? No questions? No questions on Zoom? Well, then let me get Tim to introduce our speaker tonight, Steve Levin. Tell us a little bit about Jupiter. Juno at Jupiter.
That's right. Oh, boy. Oh, come on. You've all seen me before. So, Steve Levin was one of my colleagues at JPL. He's still there. I'm long gone. He's the chief scientist for the Juno spacecraft currently spinning around Jupiter. He's going to tell us all the secrets of the universe, the secrets of Jupiter, the alien life you can't talk about in the atmosphere of Jupiter, all that good stuff. He's the chief scientist for the mission, and he's one of the lead investigators on the microwave radiometer that studies the atmosphere. And he always knows the latest and greatest stuff on Jupiter. So, Steve, you're on. I guess you have the lapel mic. I'm going to turn this.
Can you hear me? Yes. Well, that was good because at least part of what Tim said was true. Okay, so I'm going to tell you about some of the stuff we learned from Juno at Jupiter. And as usual, I'm going to try to race through way too much material and save time for questions at the end because questions are the fun part. And I think it's been a couple years since I talked to this group about Juno, which means that I have to repeat some things, but I don't want to repeat too much because some of you might remember something and so forth. So we'll kind of play it by ear a little bit, but I also want to point out the mission website has all kinds of cool stuff, which I will show you. I guess actually let's do it right now for at least a minute. So I'm going to bring up it. The website is missionjuno.swri.edu, but you can just Google Mission Juno and you'll find it. And I want to show you a couple of things. First of all, if you want to see the latest and greatest amazing pictures from JunoCam, you just click over here. Oh, I got to show you the better. Is that pretty much filled screen? Okay, so now it's a little hard
It's
for me
not
to get
filling
to.
my
But
entire
let me go back
screen.
to the beginning because I want you to see what it looks like when you get there. So there's a section called Featured Images, and it shows basically what we thought was the coolest pictures from JunoCam, the visible light
Excuse
camera
me, but
on
we
Juno.
need
And
the Zoom people
the other
need
thing you
the
need to know
entire
about
screen
that
shown.
is JunoCam is an outreach camera designed for the general public to do all the work. So we just dump the raw data on this website and we let people pick it up and make their images and play with everything from putting together the slivers into big images and combining the colors to make a color image, to just playing with the contrast and editing and photoshopping and putting ducks in the middle of Jupiter or whatever they want to do. And there's a system for uploading those and letting the rest of the world have them, and people often play with the previous images, but we found some amazing stuff done by the general public. And I'm basically not going to go through any of those because you don't need me for that. You can do it yourself. And likewise, I wanted to show you, if you go to the menu here on that same website and you look for the thing that says News, we've got sort of one-pagers of what we think of as our most interesting or exciting science results. So it's not all of them because all of them would be way too much work to try to get into the website, and I'll show you in a minute. We have tons of science, but there's always cool stuff here, and each one of these is sort of a one-pager. So I'm generally not going to talk about those too much either because, again, you can get to it at the website, although, of course, you're all welcome to ask me questions about anything. Okay.
Spencer is suggesting you put that in full screen mode if you're going to keep doing it.
No,
for
I'm
whatever reason.
done with the website already. I'm going to go back to slides and show you if I can make it work. Hey, we got it on the right screen and everything. Okay, so what I'm going to do is I'm going to run through a little bit about what Juno is supposed to do and some of what we've learned and where we're going, and hopefully answer questions about other stuff that you guys are interested in or things I didn't explain well enough or explain too well or whatever. But first, if I can make this work, there we go. We ought to talk about why did we bother sending a spacecraft to Jupiter, because it's a lot of time and effort and money, and you don't do that without a good reason. And basically what we were trying to do is figure out these four things. The most important one is the origin of Jupiter, and from that, the origin of the solar system. So if you look at our solar system, some of you will have heard me say this before, 99 point something percent of the mass in the solar system is the sun. If you look at what's left over from the sun, more than 2/3 of the remaining mass is Jupiter, all by itself. It's more than twice as massive as everything else in the solar system other than the sun. And it formed first. So in a very real sense, Jupiter formed out of the leftovers from the sun, and everything else formed out of the leftovers from Jupiter. So if we want to understand where the solar system came from, how did it form, how did we get here, we have to understand how Jupiter formed. And even though it's the largest planet in the solar system and it's been studied for 500 years, it's one of the very first things anybody ever looked at with a telescope, until Juno got there, we really didn't know that much about what lay below the clouds. What you see from the Earth when you look at Jupiter is you see an equatorial view because it's far from the sun and it's more or less got its poles pointing out of the ecliptic. So you only see the side, and you really only see the tops of the clouds. You don't get to see underneath the clouds. So the main goal of Juno was to get very close to Jupiter and look down through those clouds in a variety of ways. So the way we get very close to Jupiter, even though it's surrounded by enormous radiation belts, high energy particles trapped in its enormous magnetic field that can fry the spacecraft and break everything, the way we get really close is, as shown in that picture, fly in an orbit that starts out really far from Jupiter, comes in over the pole above the radiation belts, because they're sort of like a donut around the planet, just like the Earth's Van Allen belts, only a lot stronger. Dive in over the pole, underneath the radiation belts, super close to the equator, and out the other side. And that lets us get really close to Jupiter without the electronics getting fried. And we were either smart or lucky that the predictions that we made that said there would be a gap in the radiation belt between the radiation and the planet were right. We really do get to fly through that. But that's what we did. That got us really close. And then what we do when we're close is we can use gravity, because gravity comes from the entire planet, including the deep inside. So we can measure how fast the spacecraft is falling, turn that into a measurement of what the gravitational field is that's causing that, and use that to deduce what's going on inside. We can measure the magnetic field because it comes from an ocean of liquid metallic hydrogen deep inside the planet. And I just have to stop every time I say that and point out liquid metallic hydrogen. So we're talking about hydrogen gas, the lightest element there is, right? If I released hydrogen here in the room, it would float up into the sky. And Jupiter is so massive, the conditions are so extreme, that not only is that hydrogen gas squeezed so much that it makes a liquid, but in a sense, the electrons are squeezed right off the atoms. It conducts electricity. It's a liquid metal. And it's the swirling motion of that liquid metallic hydrogen down inside Jupiter that generates the magnetic field. So by measuring the magnetic field, we're learning about the liquid metallic hydrogen, so we're learning about the interior of Jupiter. And then a microwave radiometer, that's my favorite toy. So that's a radio receiver that's looking at the natural radio emission from Jupiter. But Jupiter's hotter on the inside than it is on the outside, because it's still cooling off from its heat of formation 4.5 billion years ago. That's just how big it is. And it glows. Like anything else that you heat up, it glows. If you heat something hot enough, it glows white hot. If it's not quite that hot, it glows red. If it's a little cooler than that, it's infrared. If it's cooler than that, most of its energy is coming in the radio. And that accounts for at least the top of Jupiter's atmosphere. So when we look at Jupiter with the radio, 6 different channels see 6 different depths into the atmosphere. They're seeing the glow of Jupiter. And so we're penetrating beneath the clouds and learning something about the interior. In this case, kind of shallow interior compared to the other parts of our deep exploration, but still much, much deeper than we'd ever seen before. And then a whole bunch of instruments. I'm not going to go through them one at a time because we only have an hour and this isn't the fun part yet. But the idea is put those things together, try to understand the interior of Jupiter, try to understand what it's made out of, because that tells you about how it formed. Study the atmosphere, things like how does the Great Red Spot work, where do the belts and zones come from, and how deep do they go. Study the magnetosphere. Remember, it has this enormous magnetic field. We're in a great orbit to study the magnetic field because we start far away, we come in over the pole and come out the other side. That means we're crossing all the magnetic field lines. So we have experiments on the spacecraft to measure the particles that are hitting the spacecraft at the same time as we have cameras in the ultraviolet and infrared and visible that can look down at the poles and see the aurora where the particles are hitting the upper atmosphere. So that's the big picture for what the spacecraft is supposed to be doing. We launched it in 2011. We got it to Jupiter in 2016. This is a blow up of the parts of the orbits that are close to Jupiter. And the point here is our first orbits were, just like I said, come in over the pole, really close to the planet near the equator and out the other side. But Jupiter's not a perfect sphere, so the orbit has been migrating. What's called the line of Apsides has been shifting. What you can see is our closest approach started out near the equator and it's moving north, and the apogee of the part far from Jupiter started out near the equator and is moving south. So these orbits, marked in black and white more or less, are our prime mission. What the orbits we originally promised NASA we could make work and that we were given money to do. And then after that, we got approved for an extended mission where we got to fly by Ganymede and eventually past Europa and then Io. And now we're in here in the green part of this. So we're no longer kind of come close to any of the satellites because the orbit is twisted around too much, but we got data on those that I'll talk about a little bit. And the Perijove is moving north, which means instead of studying the equator really well, pretty soon we'll be studying the North Pole really well. We're already pushing pretty far north, and we've learned some really great things because, among other things, we got the first good pictures of the North and South Pole of Jupiter. And just if you haven't heard me say it before, like everything else that we found with Juno, it was a surprise. It didn't look like what we expected it to look like. All right, so that's about all the overview I'm going to do about the mission, unless somebody asks me questions. I just wanted to show you that there's way too much science for me to tell you all the science in one talk. And the easiest way to do that was a little summary here of the mission itself, the things we flew by, and all those pictures at the bottom are science journals and popular journals where we got the cover. I didn't bother trying to list everything, every article we published, because at this point it's probably 1,000 or so. But if I haven't missed one, this at least is all the journal articles that wound up on the cover of the journal. So way too much science for us to talk about all of it. And instead, I picked a few topics that are, my opinion, what's more interesting or more earth-shattering or whatever, or just newer. And we'll talk about each of these and then whatever else you ask me questions about. So we'll talk a little bit about the formation and evolution of Jupiter, because that's why we went there. We'll talk about, we discovered, one of our discoveries is that Jupiter's interior doesn't look like we thought it would. So what we expected of this 300 Earth mass planet was down in the center, there'd be a dense core where the heavy stuff sunk to the middle of somewhere between 3 and 20 times the mass of the Earth, all in a dense core right at the center. And what we found is, yeah, there's a core, and yes, it's denser than the rest of Jupiter, but it's not that dense. It's taken up maybe half the radius of the planet, and it's got fuzzy edges to it. So that's a big puzzle as to what's going on and how did that happen. Did it form that way? Did some giant impact hit the planet and stir it all up? Did the composition of the planet actually turn out to be something different from what we expected? So that's a big mystery that we're slowly coming to terms with, and people have ideas about what's going on. I'll show you a little bit about how we got to that. The weather layer is much deeper than the clouds. So what everybody, and I mean everybody, expected before we got to Jupiter with Juno was it's a giant ball of gas. Get deep enough into the interior, it's liquid, but it's still a fluid, right? So it should be well mixed down in the interior. It's spinning around every 10 hours. It's deep enough once you get below where the sunlight can reach and below where the clouds form, where the temperatures are high enough that nothing condenses. Everybody thought, okay, we're going to get beneath the weather and it'll be sort of like the deep ocean and things will be mostly well mixed. It's not what we found. We found as deep as we can see with the microwave radiometer, we still see structure. We see stuff going on way deeper than where the sunlight reaches and deeper than the clouds. So that's a mystery as to what's going on and how does Jupiter do that and why. So I'll show you a little bit about that. The belts and zones, it's an astronomy club. Most of you know what the belts and zones are, right? Jet streams in Jupiter's atmosphere moving in opposite directions. It was a question as to how deep they go. It turns out they're around 3,000 kilometers deep, and they project on cylinders rather than radii. And that, on cylinders rather than radii is not a big surprise. That was one of the possibilities that people considered, and it turned out to be right. And the 3,000 kilometers is a really interesting distance into the planet, because if you look at the properties of hydrogen gas, molecular hydrogen, when you go down to a depth of around 3,000 kilometers, under those pressure conditions, you're not yet making liquid metallic hydrogen or anything. It's still hydrogen gas, but it starts to conduct electricity at about the level of salt water. So the idea that the belts and zones are happening at the top and start to disappear at the depth at which they start to maybe conduct electricity is really interesting, because it suggests they're interacting with the magnetic field, and in fact that's what we've figured out. We think we understand that one now. We found vortex crystals in the north and south poles, so I'll talk about that a little bit and tell you what a vortex crystal is. And we did a bunch of stuff with the magnetosphere and the planet and its satellites, and that's complicated, but I don't want to leave it out because there's so much fun there. And then I showed you already, if you go to the website, you can find lots more about what we've seen. So don't despair at the fact that I'm only showing you half a dozen or so out of the probably several hundred things that we found. Okay, but let's at least start with the formation of Jupiter, because that was our big mission. That's a really important thing we're trying to do, and it was a puzzle, and it is a puzzle. So what we know is Jupiter is basically made up of the same stuff as the sun, and that shouldn't be too surprising if it formed out of the same cloud of gas and dust that formed the sun. And as I mentioned, how it formed tells us a lot about how the solar system in general formed. And we knew this for a long time. So back in the 90s, the Galileo spacecraft, one of its main goals was to drop a probe into Jupiter and measure the composition of the atmosphere to try to figure out how things formed. And I love this picture of the probe because it looks like some kind of Art Deco science fiction thing from the 50s. But that's the real object that really did get dropped into Jupiter. And what we found back around the turn of the century was that the heavier elements in Jupiter, many of them, as shown on this plot, were enriched by about a factor of 3 or 4. So what I mean by that is you take something like, say, the first one there listed as argon. Take argon. Look at how much argon do you find in the sun compared to the amount of hydrogen in the sun. So take that ratio. And then go look at Jupiter and say, what's the ratio of argon to hydrogen in Jupiter? If it formed from the same cloud of gas and dust that made the sun, and formed in sort of the same way so that it got essentially all the material in the same concentrations, all those ratios should be 1. They should be the same, right? If, on the other hand, heavier stuff formed first and clumped together, and then when it had enough gravity, it pulled in the lighter stuff, then the ratios should depend on the volatility. Things that are lightweight and easy to escape, there should be less of them, and the heavier stuff, there should be more of them, and so all those ratios should move around. But what we found with the Galileo probe was all these ratios around the same, around 3 or 4 times what's in the sun. So that's telling you that all the heavy stuff other than hydrogen and helium came in at more or less the same ratio as in the solar system, and the hydrogen and helium got left out until later, and Jupiter didn't get as much of them. That was a mystery, and the key number there to figure it out was the water content, because in the early solar system, the most abundant elements are hydrogen, helium, and oxygen in that order. So the most abundant solid by far is ice, is water ice. If things are cold enough for water to be a solid, it's the only solid around, more or less. I mean, there's other stuff, but it's by far the most abundant one. So if that's right, and if Jupiter formed from solid chunks of ice or solid objects colliding together and sort of sticking until they had enough mass that their gravity could pull in the hydrogen and helium, then what you'd expect to find is a bunch of ice that carried in everything else. There should be a lot of water in there, a lot of oxygen in Jupiter's atmosphere. And if it formed super cold, far from the sun, where everything kind of stuck together, then the amount of ice you needed would be different compared to all the other heavy stuff than if it formed warmer, where things didn't stick to the ice as well, and the ice has different chemistry. So the water was a key number to figure out Jupiter's origin and formation. And what we found with the Galileo probe, which dropped down to below the cloud level that everybody thought the year 2000 would be enough, was it wasn't getting a stable water number. It found very little water, and the amount of water it found was still changing, even when it got as deep as the probe could go before getting crushed, which was about 22 bars, 22 times the pressure here on the Earth. So eventually, people worked out, the scientists worked out the idea that, well, it happened to fall into what's called a hotspot, a 5-micron hotspot. So a place on Jupiter that is like the Sahara Desert of Jupiter. It just happened to be a place with very little water, and it didn't go deep enough to get below that and sense the global water content. So NASA said, okay, we're going to send another mission to Jupiter, put out an announcement of opportunity, Jupiter Polar Orbiter with probes, plural. We'll send a bunch of probes, and some of them won't hit hotspots, and they'll go deep enough, and we'll get the water. And Juno, we proposed to that, and we proposed to that opportunity of polar orbiter with probes, a polar orbiter with no probes at all, because we said no matter how many probes you put, it's only going to be a handful, and it's not going to give you the whole story, and it won't go deep enough. We're going to use the microwave radiometer and do remote sensing, but we're going to see much deeper, and we'll get the water content. So that's what we did, and you can see different ideas of how Jupiter formed and how much water you'd expect. If it's way up here, then Jupiter formed warm, somewhere near where it is now. If it's in the middle here, like all these other things, then it implies cold, and it formed really far from the sun and drifted in, or maybe the planetesimals that formed it drifted in. And if it's really down here where the probe found hardly any water, then none of the theories work and we need to make something up. So what we found, that's this picture over here, if you can see my arrow in the bottom part, and this is a relatively recent result because Jupiter was way more complex than we expected, but we eventually were able to show that the water content comes out in about that middle range. So we think Jupiter probably formed from icy planetesimals or far from the sun where it's quite cold. However, there's a wrinkle, and that is that because we found the atmosphere much more complex than expected, so far the water number we have is only at the equator at Jupiter, and we haven't shown that it's really global. And that's if you take the microwave radiometer and look into Jupiter at sort of skin depth, but still now 100 bars instead of 20 bars, way below the water cloud, where it should have been well mixed. What we find is all this structure, and it's just not well mixed. The only place that it really looks vertically mixed is at the equator. So that's the place that it was easiest to get the water content. We have that. We're now working on the water content up near the pole, because that's the next easiest place to understand it. But assuming that comes out the same, it tells us the formation story that we started with of the three possibilities of something's crazy here, or it formed cold, or it formed more or less warm where it is. The one that fits is it formed cold. But the problem is that, remember I said we were going to measure the core, and I mentioned that the core is big and fuzzy, and the interior of Jupiter doesn't look like quite what we expected. And the folks who study the interior of Jupiter using the gravity, the answers they're coming up with is a lot less of the heavy material than what we see in the upper atmosphere. So there's two possibilities, basically. One is we don't understand the physics, the equation of state of hydrogen, what its pressure and density profile are when you get to those extreme circumstances, and there's something wrong there. So we have people working off doing experiments with giant lasers where you implode a little bit of hydrogen and try to study it, because you hit it with this enormous amount of energy, and before it explodes, it implodes. You get to really high pressures and measure it and try and see if we really get the equation of state right. So fundamental physics, that's one possibility. And the other possibility, which I think is really cool, is the possibility that the very upper atmosphere of Jupiter, that is all the part we can reach at down to pressures of 1,000 times the pressure here on the Earth, is different composition than the interior. So think about what that would have to mean, right? That would mean you have more of the heavy stuff at the top of the atmosphere than you do down in the center. So somehow, for 4.5 billion years, it remained segregated. Or somehow, in the last few 100 million years, the top got contaminated and it stayed segregated. Or there's some process that kicks the heavy stuff up to the top and separates it that way. It's a very weird thing to be happening if that's really what's going on. But in many ways, that's the best explanation. It doesn't require that we have misunderstood the physics in some way. And we know from the microwave radiometer, not only did we get a water detection and get an amount of water that kind of matches, but we were able to measure the sodium and potassium in Jupiter's atmosphere really deep, about 500 bars. That's about the deepest thing we see with the microwave radiometer. And we found very little sodium and potassium. They're less than 1 time solar. So that's kind of consistent with what the gravity folks are telling us about how we might be missing the heavy stuff in the interior and the top of the atmosphere is somehow contaminated if the dividing line is way up above, lower pressures than 500 bars, only a few hundred kilometers into Jupiter. Still an open story. We don't know the answers. What we know is it's a really interesting puzzle and mystery. And we got more than we bargained for in trying to understand the formation of Jupiter, but that's the fun part. So we can talk about that more if people ask me questions, but I'm going to move on so we don't take forever on just the beginning. More major discoveries. We see storms with the microwave radiometer. We can see in 3D because the 6 channels see 6 different depths and we look at different angles. So we get kind of like a CAT scan. And we see some storms that go much deeper than others. So we're trying to understand that. But in general, the storms on Jupiter seem to have pretty deep roots, much deeper than here on the Earth. But of course, Jupiter's atmosphere is enormously bigger. And we saw, remember, all that complexity, and we don't have an explanation, a good explanation really, for why there's structure way below where the sunlight can reach and below the water cloud. But one of the proposed possibilities is a thing we call mush balls. And the idea is on Earth, when you have a hailstorm, what's happening is the wind carries water droplets up high where they freeze, and they fall back down again, get caught in the wind, get covered with liquid water again, and carried up again and freeze again. And so you get bigger and bigger pieces of ice, hailstones, until finally they're too heavy to get lifted up by that updraft, and they fall down to the ground and it rains ice here on the ground. That's a hailstorm. So on Jupiter, the atmosphere has ammonia in it. So it's sort of like Windex, our antifreeze. And you can get droplets of water with ammonia dissolved in them so they don't freeze very easily. But the outside gets coated with water that does freeze. And updraft can carry it up, freeze, fall back down. Same thing as with a hailstone, but now you've got ammonia tied up in these balls of sort of liquid in the center, mushy ice on the outside that we decided to call mush balls. If that's what's happening, that would explain why the structure goes way deeper than the water cloud, because these things are going to fall down. And in order for it to work, they have to also rise up way higher than where you'd expect to find frozen water. And that gives you an interesting possibility, because what it takes to make lightning is all 3 phases of water. In order to get a lightning bolt, you need the static electricity to be carried by ice, and you need the liquid water and the water vapor to make the dynamics work. So that says if these mush balls are happening, you should find perhaps lightning at shallow depths, higher than where you would otherwise expect to be able to find it, because the mush balls will be carrying ice up much higher in the atmosphere than where you'd expect to find water ice. And sure enough, we found shallow lightning on Jupiter. Our Stellar Reference Unit, which is a camera designed to do navigation, to look at the stars, it's a dark sky camera, was used to look at Jupiter on the night side in the dark, and it saw lightning bolts or lightning flashes. And from the size of the flashes, you can tell that they're shallow. If they were deep, they would spread out in the clouds and look bigger than what they look like. So we see shallow lightning, so that's a supporting piece of evidence for this whole mushball theory, that maybe that's what's going on for why the atmosphere is so complicated. Okay, so I want to get to vortex crystals because just the name is really cool. So one of the very first things we discovered were circumpolar cyclones. You fly over the North Pole, infrared, see is on a pole rounded a cyclone, sort of almost a square shape, a rectangular shape. Those cyclones have been there the entire time we've been at Jupiter, since 2016. Every time we fly by the North Pole of Jupiter, we see that same set of cyclones. So it's a stable formation. And if you look at the South Pole, you see a central cyclone surrounded by 5. And that's pretty much been stable the entire time, although we did see at one point a 6 cyclone kind of push its way in and then get shoved out again. So this pattern of cyclones around the poles, circumpolar cyclones, forms what's called a vortex crystal. It turns out that if you take a tub of glycerin or something and you spin it the right way, that it'll make swirls in it, and the swirls will indeed make patterns and that can do something like that if the conditions are right. What you need is for the cyclones to spin mostly one way, but with an outer wall that spins the other way so they don't eat each other up. And their size has to be right so that as they drift north, because in a rotating planet, the cyclones will drift north, or ones near the South Pole will drift south, so that as they drift north, their size has to be right to fit the number of cyclones there. So we've done the math, and all of it works, except for explaining why they have the size they have and why they're different in the north and the south. That's still kind of a mystery. But remember, we have the microwave radiometer that can see beneath the clouds, can see depth in the atmosphere. And our perijove, our closest approach to Jupiter, is moving further and further north. So now in the extended mission, we're able to look at the North Pole at least and see these circumpolar cyclones in the visible, the infrared, and the radio. And seeing them in the radio gives you a really interesting result. Now, this stuff that I'm showing you now is public in the sense that I haven't been told not to show it to anybody yet, but the papers aren't published yet. We haven't dotted the I's and crossed the T's and convinced ourselves and peer reviewers that it's 100% right. So take what I say with a little bit of grain of salt. However, the upper left picture, that's a Juno composite of the circumpolar cyclones at the North Pole. And what you can see is they look generally similar, but you can see sort of two kinds. There's one that's a kind that's covered with clouds and a kind that doesn't have too many clouds. And the central cyclone is maybe in between, but mostly looks like one without clouds. You look at it in the infrared, and you can see the same story. In the infrared, when there's no clouds, you're seeing deeper into the atmosphere, so it looks warmer. So that's the yellow ones. And the ones with clouds are a little cooler. And you can see different structure and so forth. Basically, two kinds of cyclones, with maybe the central one being a third kind, or at least somewhere in between them. And you look at it in the microwave, and that is, the middle one here is our highest frequency channel. That's our shallowest look, looking a little bit deeper than the infrared. The next one to the right, that's a little deeper than that, half the frequency, twice the wavelength. The next one is from channel 6 to 5 to channel 4, looking deeper than that, and then channel 3, looking deeper than that. And I'm not showing you channels 2 and 1 because their beams are bigger, their resolution's not as good, and we're not yet close enough to the North Pole to get really good images from them. But what you can see here is the cyclones don't all look the same, and the ones that seem to have clouds are the ones that are bright in the radio. Presumably that means they go deeper. And the ones that don't have the cloud cover, that look just as strong in the infrared, they just look like they don't have clouds on them. You hardly see them at all in the radio. And the central cyclone, we're either not seeing it, or I think there's actually a hint here that it's colder instead of warmer than the stuff around it. So these circumpolar cyclones that make up the vortex crystal in the north of Jupiter come in at least 3 flavors. Very interesting, bizarre kind of stuff going on to try and figure out these storms. And that's our latest puzzle that we're working on in the atmosphere, is to try to understand, why are there 3 different kinds? Why is the central one different than the other 2? Why does some go deeper and some not? And is that related to why some have cloud cover and some don't? And different temperature anomaly, do they stir up to different depths? Are they just stronger even though they don't look much different in the infrared? Is the microwave telling us that some of these are stronger than others? Or is it telling us that they're sort of the same thing, but they go deeper, and when they go deeper, you get something different? And why do they go deeper? So lots of questions, not a lot of answers yet. It's the latest puzzle, but it's a really interesting thing to be studying in Jupiter's north. I'm going to move on a little bit to the magnetic field. This is actually a video that's been around for a while, but it does illustrate the magnetic field of Jupiter. Planet shows it to be blue. As far as we can tell, it's got nothing to do with the great red spot, drifts around the planet at a different rate and all of that stuff. But it's just weird. And then if you keep going and look at this, now that we have really good measurements of the magnetic field, what you see is the south does kind of look like more or less a dipole field like the Earth's. But the north looks crazy. It's just every which way, all this little components and stuff. It's a mess. So that's another big puzzle as to what the heck is going on and how does Jupiter manage to make a magnetic field that way. So we think that most of that extra weird structure is perhaps not coming from the liquid metallic hydrogen that generates the bulk of the field, but from shallower layers where the gas doesn't conduct the electricity as well, but conducts it enough so that motions in the gas affect the magnetic field. And remember what I said about the belts and zones, right? At that depth of a few thousand kilometers, we see the belts and zones stop. And I don't think I have the map in this deck of slides, although it's one of those things on the website if you look under news. But what we've seen is we can actually see the magnetic field being distorted by the winds from the belts and zones. So remember, each of the belts and zones, they move opposite directions at a couple hundred kilometers an hour. And if you look where that great blue spot is, what you see when you map the magnetic field in detail is it's distorted, and it's distorted to the right where the winds are blowing to the right, and it's distorted to the left where the winds are blowing to the left. So we think a lot of this structure has to do with the winds blowing around the magnetic field, and we're actually seeing the magnetic field change very slowly due to the winds moving it. And of course, they're equal and opposite. The fact that they're exerting a force on the magnetic field means it's exerting a force on the winds and slowing them down. And so that explains why the winds only go as deep as where they get deep enough to interact with the magnetic field. So that story is starting to come together and make some sense, but it still doesn't explain why the north is so different from the south. That's just a mystery, and we found lots of examples on Jupiter where it's asymmetric. The northern hemisphere doesn't look the same as the south. I mean, you know a little bit of that from what you can see from Earth because the great red spot's in the south and there isn't one in the north. But it turns out there's more lightning in the north than the south. The magnetic field is much more distorted in the north than the south. The aurora is different in the north than the south. Jupiter just has a lot of asymmetry, which isn't yet explained. Okay, I'm going to give short shrift to the magnetosphere stuff, but we can come back to it if somebody has questions. I'll just point out that we see that the aurora that we've always known about as seen from the Earth look different when you get to fly over the pole and see them when you're not looking at the side of Jupiter that faces the sun. Remember, we're closer to the sun than Jupiter, so we only see the sun side. And turns out when you fly over the pole and you look at the dark side, a big part of the aurora shuts off at night. So that was an interesting puzzle. And we see footprints from Io. The moons of Jupiter interact with the magnetic field. They cause the particles streaming down the magnetic field lines to change, and you get these lines on the planet that we knew about before Juno that are caused by interaction with the moons. But what we didn't know that we learned with Juno, when you look at it in the ultraviolet and the infrared, is you can see all these bumps in the line. So there's, we think, waves coming up and back and forth, causing this interaction, and the tail actually splits into two and has to do with how the the waves, the plasma waves are traveling in Jupiter's magnetosphere. So lots to talk about there, but not enough time, so I won't. Ganymede, we flew by Ganymede. There's a beautiful picture. This is another JunoCam image. So Gerald Eichstadt, who's one of the volunteers, he lives in Germany and has a day job that he says he can't talk about, but he's really good at image processing and fluid dynamics. And he tends to take the raw stuff, put them together into pretty good images with great attention to detail and a sort of computer savvy pipeline. And then other people take what he's done and make them prettier or bring out details or things they want to emphasize. So in this case, Matt Swift worked with Gerald's data and made this beautiful image of Ganymede. It's taken by Juno. But I'd rather talk about the microwave radiometer looking at Ganymede. Even though the image isn't as beautiful, just like we can see through the clouds with the radio, we can see through the ice with the radio. So Ganymede's the first moon we flew by with the microwave radiometer, and we got brand new information, brand new instrument at an object that had never been looked at that way before. And what we see is the spectra on the left, which obviously needs a lot of explanation to be anything more than a bunch of lines. But what you're looking at is the brightness at each of the different 6 channels for all the different spots on Ganymede where we looked. And different terrain looks different. The brighter terrain in the optical is also reflecting more in the microwave. So there's cracks in the ice, and the white parts have more cracks than the dark parts. And the newest things like Tros crater there, that blue line pointing at the white spot, that's a crater on Ganymede called Tros crater, is the coldest that has the most reflection. And we learned something from that so we can learn about the thickness of the ice shell, because remember, we're measuring temperatures. Changed on me on its own. We're measuring temperatures, and underneath the ice there should be liquid water down at the bottom, but we don't know how deep you have to go. It's heated from the inside by tides from Jupiter, right? But we don't know whether it's a priori, whether it's 10 kilometers or 100 kilometers or 500 kilometers from the top down to the water, except that now with the microwave, we can see the temperature gradient and use that to deduce how thick the ice shell is. So it's somewhere around 75 kilometers thick, which is a new result and pretty interesting for Ganymede, but going to be a lot more interesting at Europa, because Europa, everybody's excited about maybe there could be life in that ocean under Europa, and we're sending Europa Clipper, a mission there to study things, and someday we hope to send a lander that's going to land on the ice and try to get through the ice and measure the water or measure plumes of water that come splashing out. So we'd really like to know how thick that ice is and how far it is to the water. The spectra on Europa look really different. We're still working on that. I'm the one writing that particular paper, and it's not submitted yet. So I'm not going to promise that these results are right, but the general idea that we're seeing is, if you look at this spectrum that I'm pointing out with the arrow, this part of it on Europa, what you can see is the shallow channels, that's the high frequency channels, look warmer than the next one down, which is still warmer than the next one down, and so forth. It's getting colder as you go deeper. Now we know the ice itself is at best staying the same, or probably getting warmer as you go deeper, because there's liquid water underneath it. So what must be happening is we're getting more and more reflection as we go deeper. So that tells us that there are pores in the ice, bubbles, that reflect the radio, and then it levels off, which tells us that those reflectors have a size that's comparable to or smaller than our wavelength. So centimeter size bubbles like this in the ice cause that signature. And then the ice from other things we're looking at must be comparatively thick compared to where the range of estimates. The range of estimates for how thick the ice is before Juno, somewhere between 3 and 30 kilometers thick on Europa. And we're going to wind up claiming that it's on the thick side of that. And I won't quote you a number yet, because it's not even submitted, let alone peer-reviewed yet. But we're learning exciting things from taking a brand new instrument and using it in a brand new way. And then we flew by Io as well a couple of times. We get to measure Io's gravity as we go by, which helps us distinguish between two really interesting models of what's going on with Io. Basically, we know Io is covered with volcanoes. The infrared camera has been studying those volcanoes from a distance for years now. And there are two ideas of what Io looks like underneath the surface. One is, probably the prevailing one really, is a magma ocean, melted rock. There's enough tidal energy from Jupiter distorting Io that it actually melts the rock and you get these volcanoes. And the idea is that there's an ocean of melted rock, a shallow ocean. And the other model is not enough to make an ocean of melted rock, but rather just sort of kind of like a porous sponge kind of thing where it's mostly solid, but there's enough melted rock to make the volcanoes. So we will distinguish, I claim we actually have distinguished between those two models with the gravity measurements. But I'm not going to tell you the answer here that I think we know because it's not yet published, and you guys are putting a video out where everybody on the web can see it, and the journals don't like it if you submit the paper and then tell the world the result before they've had a chance to peer review it. But watch for that. In a month or three, you'll probably see the result. And on top of that, I'll just point out where with the infrared camera, we've had a bunch of flybys of Io that were not as close as these 1,500 kilometer ones to get the gravity, but the camera can still take pretty good images. And we see lava lakes on Io where what you see is it's sort of warm in the center, and then the edge of the lake is hot like molten lava, and then the surrounding terrain is cool like icy rock at the surface of a moon. So we think what's going on there is like there are some lava lakes like this on the Earth where there's a crust over the top of the lava, and it moves a bit up and down, so the crust gets broken at the edges of the lake. So you have no crust right at the edges where you see the hot lava, then you have what might be only a few centimeters of solid rock covering most of it, and it's hot in a pretty interesting structure. So we have microwave data that we hope we can support that theory with and try and check it. But that's what it looks like from the infrared. So almost done with the main stuff before we do questions. I'll just point out radio occultations. We are now, the orbit's changing to where we go behind Jupiter as seen from the Earth. And that's both a scary thing because you're out of contact and out of the sunlight for part of it, and it's solar powered and all of that. But it's also a really cool thing because as the spacecraft goes behind Jupiter and when it comes back out, that means the radio link is passing through Jupiter's atmosphere, which means we can measure the composition and the density, particularly the density of the atmosphere, by looking at how the radio link gets distorted. So that's just started happening. It's going to be happening every few orbits for quite a while now. And this is a little map of Jupiter where all the ingress and egress places are, where we go behind the planet and come back out. So all the places where we're going to get to measure the density of Jupiter's atmosphere and the ionosphere of Jupiter, and learn a whole lot more in ways that you couldn't do without an occultation. Then finally, before questions, I'll just remind you, I gave a talk about Gabbert not too long ago. Goldstone Apple Valley Radio Telescope, kids and citizen scientists running a big 34-meter radio telescope over the internet and doing real science, and they are partnering with us on Juno because one of the things they observe is Jupiter, and there's actually papers published by students that have been used by Juno to help improve our science results. And you all can get involved in Gabbert if you want to as well. Just Google GAVRT. Okay, that takes me to the end of what I already had prepared that I wanted to show. But I would love to spend a while answering questions and talking about whatever you guys want to talk about. Yeah? You might need the microphone, I guess. In fact, you want to be in charge of the mic?
I can. So the liquid metal hydrogen, does that go all the way to the core?
No. So we're pretty sure that somewhere around 70% or so of the radius of the planet is where it's dense enough at a couple million times the pressure here on the Earth to start making liquid metallic hydrogen. And then the denser material, the heavier stuff that's not hydrogen, should have sunk to the center, and there should be a core down below that, below the liquid metallic hydrogen. There's a little bit of a question about whether that mixes with liquid metallic hydrogen and you could have sort of a slushy region. I mean, it's hard to even talk about solid versus liquid when you're talking about pressures that are, 10 million times the pressure here on the Earth and temperatures, but it's a dent on it, or there is hydrogen.
What do we think is if it's not hydrogen?
So it's the heavier elements that should have sunk to the bottom. And the ratio of those is the thing that's still an open question, where our gravity measurements are suggesting the relatively low ratio of heavy stuff. So something like similar metallicity, you call it. If you're an astronomer, anything that's not hydrogen and helium is a metal. And so metallicity of somewhere around 1, so similar to what's in the sun, is what the gravity folks are saying. And all the measurements of the shallow atmosphere say, no, it should be 3 or 4 times what's in the sun. So that's still a conflict. But even if it's only the level of what's in the sun, that's still quite a bit of material down in the center. It's several Earth masses.
Dave, do you have a question?
Yeah, I do, but I'll take the mic around to people for you, okay?
Hi, thank you so much for tonight. This is great.
My pleasure.
My understanding is that Jupiter is, because it's so large, it's actually a protector of asteroids. The asteroids hit that because it's so large before it hits the Earth. So what happens to an asteroid if it goes into Jupiter, since it's not that dense?
Okay, so 2 things. One is the way that Jupiter interacts with comets and asteroids. Most of the time, they don't actually impact Jupiter. They get kicked out of orbit to further from the sun or even out of the solar system entirely. And occasionally, they get kicked inward. So the notion that Jupiter is a protector of the Earth because it keeps things from hitting the Earth is true, but it's also a little bit misleading because once in a while, it probably kicks something towards us instead of away from us. But things do, like we saw with Comet Shoemaker-Levy 9, do actually hit Jupiter, and on a cosmic timescale, what happens is they just get swallowed up. The mass is so small compared to the mass of Jupiter that the thinking until Juno started finding these contradictions was they can't really affect much of anything, and if you wait a few years, whatever they did just disappears and sort of gets mixed in with everything else. There's a little bit of caveat to that because we know we have this puzzle we don't understand, and one possible solution to the puzzle is that somehow there's enough stuff staying shallow enough that it really can contaminate Jupiter's atmosphere. And maybe what's going on is the very upper atmosphere of Jupiter, and by upper atmosphere in this case I mean to pressures of a few hundred times the pressure here on the Earth, so pretty dense atmosphere, but not for Jupiter, that maybe that thin part of Jupiter's atmosphere is contaminated and somehow the heavy stuff isn't falling in and getting mixed with the rest of the planet. So if that's what happened, it could very well have happened from comets and asteroids hitting Jupiter. Probably not tremendously recently, because we know that the solar system was filled with a lot more stuff 4 billion years ago than it is now. But we don't know, and it's pretty much speculation at this point because nobody has come up with a really good mechanism that is going to keep those things separated for 4 billion years.
Well, do we have any questions here in the audience? Okay, I'll bring the mic up to you. And then we'll ask if we have any questions that are on Zoom, okay?
Hi, also thank you for coming.
Sure.
You talked a little bit about being, as you were just talking about, being surprised that it's not a little more well mixed, and then later on about how funky the magnetic field lines are. Does that support there being a recent event of some kind that it's still settling out from?
So people have looked at giant impacts and tried to say, okay, if Jupiter got hit with something, the size of Uranus or something 500 million years ago, what would that do? And partly the answer to that is we don't know. Partly is it seems like it should stir things up more than what we see. It's hard to tune it to do just the difference we see. And also people tend to be skeptical just because there's a long history of people having things they don't understand about a planet and saying, well, it got hit with something. And impacts happen. We're pretty sure the Earth's, our moon was formed by a giant impact. But most of us are skeptical about that explanation. It doesn't mean it's wrong, it just means we're skeptical.
Spencer, do you have people on Zoom that have questions?
You have somebody behind you who's raising a hand.
Somebody
too.
do? Okay.
Yeah, there's one question that I see. It's you want me to go with this one or take the one?
Yeah,
We have one person here. Hold on, then we'll take yours, okay?
You mentioned there being some uncertainty as to the gravitational force of Jupiter and some of the composition of the planet. Did that make it difficult in calculating the orbit where you threaded the needle underneath the magnetosphere, or was it pretty straightforward?
So, first of all, I didn't do it personally, so I should let one of the nav guys say whether it was hard or easy, but they did a spectacular job and it worked really well. And it's not so much the total gravitational force that is uncertain, but rather when you look at the gravitational field overall. So, right, the planet is 300 times the mass of the Earth and it's rotating every 10 hours, twice as fast, right? So it bulges at the equator and it flattens at the poles. Then it's got belts and zones moving in opposite directions, so they all puff out or get pulled in, depending which direction they're going, and that has to do with their mass and density. Then there's a dense core at the middle, and that's going to change how it reacts to that rotation and how much it flattens and so forth. All of those things add up to slight variations in the gravity. Then there's the moons that have their own gravitational pull on Jupiter and distort it. That's going to change the gravity. Lots of other stuff like that. So what you get is when you orbit past Jupiter, the first term, what's the total mass of Jupiter? That one we have nailed really well. The next term that has to do with the shape of the planet, right? We have that nailed pretty well. But you keep going to higher and higher order terms, and you learn more and more information from tinier and tinier measurements of the gravitational field. So stuff like getting the right orbit, not really affected by this level of complexity. What the level of complexity we're talking about is very tiny motions, very tiny changes in the speed of the spacecraft integrated over the whole path of the trajectory. And to give you an idea of the level that we're considering here, I was leading the requirements team back when we were designing this for defining what all the requirements were in order to do the job. And one of the requirements we had was that the spacecraft shouldn't have any accelerations that weren't understood, because we wanted to know the acceleration from gravity, not from something outgassing on the spacecraft that would shove it around a little bit. And so we worked with the gravity team for, well, how well do you need to know things to not interfere with the measurement, right? And the answer was, we want no accelerations greater than 10 microns per second squared. So incredibly small changes in velocity can be measured with the radio signal that works for the gravity, and those are the kinds of measurements they're using to learn about the gravity, in the gravitational structure inside Jupiter. So things like affecting the orbit of the spacecraft, yeah, in principle it affects the orbit of the spacecraft, but not enough for us to care in terms of navigating. It's really about learning about the structure from those really tiny changes in the speed.
Spencer, go ahead.
All right, so there's a question from Dave Nakamoto. Does the radio occultation experiment detect polarization of the signal too?
I think, well, my off-the-cuff answer is I don't know. But I think it should. So we generally use circularly polarized radio for communications. You would expect to affect the polarization. The reason I don't know is offhand, if I think about the interaction you'd expect from the radio going through the atmosphere, I would expect it to be a linear polarization that's affected, one linear polarization more than the other, and that should cancel out if you're only doing circularly polarized radio waves. But the real answer is I don't know. We'd have to go look at, I'd have to talk to somebody who knows more about it than I do.
Right. Second question from Eric is, knowing what you know now, are there any instruments you really wish you could have flown on board Juno that it doesn't have?
Not really. So the microwave radiometer was our biggest brand new, nobody's ever done this before kind of instrument to take to an outer planet. And it's worked spectacularly well. We've learned all kinds of stuff, way better than what we thought we would get in terms of how useful it is. But it's been 20 years since it was designed, and we can do that stuff a little better now. So I wish I had a more modern one. And in fact, there's a team of us working on, building the next generation MWR. But I don't really count that as I wish I had that other instrument, because, it didn't exist back when we were putting things on. The only thing that I really wish we had brought along, and we knew at the time that we wanted to bring along, but we couldn't, is a dosimeter to measure the radiation more accurately. Not really for the science, but more for understanding what's going to happen to the spacecraft and for the next spacecraft that comes along. To know the radiation belts better would have helped Europa Clipper do a better job designing their radiation and their shielding and all of that stuff. And we didn't get to do that. We actually, after we had been selected, our proposal had been selected and NASA had decided on funding and all of that stuff, it occurred to us that we really would like to add a dosimeter. And we went to NASA and said, for the next mission, it would be really cool if we had a dosimeter here. And here's how we can do it. It would only be this many $1 million. And they said, thanks, but no. They didn't want to spend the money. Maybe they were right. I don't know, maybe they were wrong, but in any event, we didn't put it on, and that's the one thing I wish we had. We're using everything else on the spacecraft to try to figure out how much radiation we're getting from, more indirect measurements than just measuring it directly. But it would be nice to have something designed to measure the radiation damage.
Other questions in here? There is a question here. Hang on a minute, I gotta get you the microphone. The people, the Zoomies, won't hear you even if you scream at the top of your lungs.
I was wondering what the frequency bands of the microwave radiometer were, and what the difference in the science was between them.
Right. So our longest wavelength, lowest frequency, is 50 centimeters, 600 megahertz. That means the antenna, the beam is fairly big. It's 20 degrees wide. That's our resolution with that channel. And the antenna basically defined the size of the spacecraft. We had to have a spacecraft big enough to hold that antenna. And our shortest wavelength, highest frequency, is 22 gigahertz. Excuse me, which is, I think, about 1.5 centimeters, so this big for wavelength. We have 6 channels, and there are factors of 2 in between. So we use them together. It's not so much that you get really different science from each individual channel as you get much better science from all 6 together than you do from any channel alone. So the way to think about that is if I'm looking at Jupiter's atmosphere, the longest wavelength, the 600 megahertz channel, can see down to pressures of a few hundred bars, so a few hundred times the pressure here on the Earth, and the tail of that distribution, because it's hotter down deep, is coming from 1,000 bars or something like that. The next channel up is seeing much shallower, so think of it as 50 bars or something with a tail that goes deeper. And the next one is shallower than that, and so forth, all the way up to the highest frequency one, which is just looking a little deeper than the infrared channel does, and maybe it's, you know, half a bar or a bar. Okay, so in kilometers, if you want one, the shallowest one is a kilometer-ish or so, or a few, and the deepest one is hundreds of kilometers. Putting those all together means you get the structure of the atmosphere. And if you use the fact that we're a spinning spacecraft, so you're looking at a bunch of different angles, that means I can compare with each channel what we call the limb darkening. As it looks straight down, you get the hottest temperature because you're looking as deep as you can see. If you look at an angle, then you're seeing shallower, so it looks colder. So it's darker as you turn towards the limb, and that's a measure of the slope, right? The gradient in the temperature and opacity. So now I have the gradient from channel 1, and I get to compare it with the absolute brightness from channel 2, and that lets me lets me separate what's due to temperature and what's due to opacity. So opacity is about the composition. What's the atmosphere made of? How much nitrogen, how much oxygen, and so forth. And temperature, of course, is about how hot it is. And those two things get mixed together if you only have one channel. But if you have two channels and you can do limb darkening, then you can kind of separate them. And if you have 6 channels, you can do a better job of separating them, and you can follow the temperature profile from deep to shallow. So it's really nice to have all 6 channels to put the story together and see the water cloud and how the temperature changes, and learn how much oxygen and how much ammonia is in the atmosphere, and see all of that structure. You couldn't do it with only one channel, but all the channels are measuring sort of similar things, but at different depths and different temperatures, and working together gives you the full picture. Does that help?
Thank you.
Sure.
More questions in here, all the way in the back.
You're going to get a workout going up and
Yeah,
down the
that's why I
stairs
do
with
it.
the microphone.
Who had their hand raised?
I have 2 questions, mainly for clarity. The first one is, how do we know that Jupiter's core has a fuzzy core? And the second question is, why were the cyclones called a vortex crystal again?
Okay, so 2 very different topics. So the fuzzy core, the reason we think it's fuzzy is when you look at that gravitational signature, if you had a dense object in the middle, right, with a sharp edge to it, which is what we originally expected, then the gravitational signature from that as it rotates would be, you know, the thing rotates like this, so you speed up and slow down as you get over the bulge, but it's at some fixed distance, and so it's got a signature in the gravity and the way the spacecraft falls around it that is determined by the density and the shape and the rotation. If it's fuzzy, then you don't get that sharp signature from it. You still get a signature, but now as the spacecraft falls, the way it speeds up and slows down is a little bit different. I'm being vague about it because the only real way to answer it is with the math, and I don't have the math with me to show. And in fact, it's complicated enough that you basically put a whole forward model together in a computer program and you know, run it and match it up with changing parameters until it matches the data that you see. But you can think of it simplistically as if I had a dense solid object and it's rotating, it doesn't, you know, it's more compressed and it doesn't stretch out as much as if it's a big fuzzy thing that's sort of soft and mushy. Then vortex crystals, it's basically a name they give. A vortex is a spinning cyclone or anticyclone, basically to have a fluid and make a little whirlpool, that's a vortex. And it turns out that if you take a big vat of material or a globe of something made out of liquid and you spin it around at the right speed, you get these vortex crystals. It's just the name they gave them. I just think it's a cool name. But you can picture how that would work, right? If you imagine, a tub full of water and you start spinning it, it's going to go round and round and make a whirlpool in the middle. But if you spin it at a different speed, it won't work very well to get a whirlpool in the middle, and you might get 2 or 3 of them that sort of form, and they're going to stay there and drift around. And if you spin it at a different speed, or you change its viscosity by mixing some sugar in the water or something so that it's thicker, you'll get different numbers of whirlpools, different number of vortices. So when that becomes a stable pattern, they call it a vortex crystal because you get several vortices and they stay in a little pattern that's stable. The fact that they exist was not a surprise. The fact that they exist on Jupiter was a big surprise. And the fact that there's 8 in the north and 5 in the south is a mystery we still don't have understood. We know that it comes from, or it's consistent with the fact that they're slightly different sizes in the north and the south. But why they should be different sizes in the north and the south, we don't have an answer for yet.
All right, thank you.
Yeah.
I have one question from Stacy. So what are some of the biggest surprises the data has shown, and will that inform the formulation of future missions?
Okay, so there's so many surprises, it's hard to decide what the biggest ones are. I'll tell you my favorites. So by far my favorite surprise is that the atmosphere is not well mixed. And that's partly because that's the piece of the science that I work on the most, but also because it means fundamentally it shows us when you go to measure something new, you're going to get surprises. Things are going to be more complicated than you expected. I mean, if I had told you, in 2015, before we got there, that there's a giant ball of gas and you're going to go down into the interior of it where sunlight can't reach and it's all the same fluid, there's no condensation or anything going on, it's just a big ball of fluid and it's spinning around. And then I said, but there's going to be all this complicated structure in there. You probably would have told me, you're nuts. That there's nothing to make the structure. There's no rocks to bump against. There's no sunlight to heat things up and cool things down. There's no reason that one part of it should be different from another. So to me, that's a warning for us that we have, as humans, a tendency to take the unknown and make it simple. If we don't know anything about it, we picture something simple. But nature doesn't necessarily do that. Sometimes we don't know anything about it, and it turns out what's there is really complicated. So I love that discovery, and I think of it as one of the biggest. On the other hand, the magnetic field being asymmetric and having all this structure was really big discovery. The circumpolar cyclones, I mean, the first time we got images of Jupiter, our very first perijove pass in August of 2017. First time we got good images over the North Pole and then the South Pole of Jupiter. We put those pictures together. The science team was all together at a science team meeting looking at the data for the first time. One of the very first things we saw were those images. And literally somebody said, "Are you sure you got the right planet?" Because the north of Jupiter just, the poles of Jupiter just don't look anything like it does from Earth, like from the equator. It's not the same color, doesn't have the stripes. It's got these sets of storms bigger than the whole US. It's just weird. So that was a really fun discovery as well. And, there's different kinds of scientists, right? There's theorists who like to put together explanations for how everything works and make predictions and so forth. And there's experimentalists and observationalists who like to measure things and hopefully throw bricks through the glass window and break all the theories, right? So it's really fun for experimentalists like me that we got to break so many theories. Trying to think else, what other discoveries are big or things that I haven't mentioned yet that were surprises. I didn't talk much about the magnetosphere, but you know, Jupiter has these giant aurora, right? So northern and southern lights, but way bigger and brighter than anything on the Earth and way more complicated. And we discovered that the acceleration mechanisms for moving the particles to make those aurora are very different than what's on the Earth. That was a big surprise. And it's complex, it's hard to understand, it doesn't make an easy news bite to be on the TV or on the internet, but it's actually a really interesting puzzle trying to understand how this works in a magnetosphere with the complicated magnetic field and a rotating planet and the solar wind and all of that stuff. And why do we get these super bright aurora on Jupiter? And why are the acceleration mechanisms that do that on the Earth different from the ones on Jupiter? So that's a big surprise as well that doesn't get a lot of coverage because it's too hard to explain.
Okay, who had the question up here?
Thank you so much for coming again.
My pleasure.
My question is around exoplanets. So, you know, we're learning so many new complicated things about Jupiter. What does that portend for, you know, when JWST finds some elements on the surface of an exoplanet? You know, can we no longer assume anything we were assuming?
Yeah, so in detail, much of what we discovered doesn't quite apply the same to an exoplanet because we're measuring slightly different things. Jupiter's not exactly the same. Most of the planets that are seen are different. You know, the Jupiters that we get to study are usually closer to their star because that's how we discover them. So in detail, I can't point to very much and say, oh, we learned this and that means you better be careful over here. But in big picture, right, it's way more complicated than what we expected. Every place where in our ignorance we put simplicity, once we got data, it wasn't simple. The message is really clear to people studying exoplanets, and that is it's not going to be as simple as you're picturing. And if you have no data and you just put together something simple to fill in the part where you don't have measurements, you're virtually guaranteed what you put in there is wrong. Early on, when we were learning all this stuff, I had a conversation. I happened to be at the airport after a conference with some people who studied exoplanets. And there was somebody who has models of the atmospheres of exoplanets. And we were chatting, and he was telling me about his model. And I said, here's what we learned at Jupiter that says you better be careful of your model. And it started telling him about stuff from Jupiter. And he literally went, la, 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 don't tell me. Because, yeah, it means that in that example, as in almost every other example of places where we can measure certain things and we have to fill in the blanks for the other stuff with theory, you got to be really cautious because it's probably more complicated than you think it's going to be.
Thank you.
Yeah.
One on the Zoom. So are there any circumpolar cyclones pulling matter downward? And if so, where's the consumed matter being spit out? And in what shape?
So are there circumpolar cyclones pulling matter downward? That was the question.
Mm-hmm,
And if
yeah.
so, what's going on with it and so forth?
Right.
So there's a bit of a question as to whether they're pushing things down or pulling things up. But in general, cyclones tend to mix the atmosphere vertically. And what they probably do is pull it in from the side at the depth of the cyclone and spit it out to the side at the top, or vice versa if it's coming in from the top and going out at the bottom. And it may even be that the different kinds of cyclones we're seeing are doing different things. But in terms of the size of Jupiter, while they're perhaps a few hundred kilometers deep, that's nothing compared to the size of the planet. So they're mixing things on a small scale, not a grand scale, because Jupiter's 70,000 kilometers in radius.
Okay, I think it's time for us to do the door prizes. So thank you, Steve.
My
Big
pleasure.
round of applause.
And yeah, I need to, if nothing else, I need to stop because I'm losing my voice here.
Okay, the link is on the Zoom in the chat for the people on Zoom, and I'll give you about 2 minutes to fill out the form.
And before we do the door prize, let me remind you, next month's meeting is Dave Nakamoto giving us the sky tour in the planetarium. That meeting cannot be Zoomed. It cannot be recorded. It cannot be YouTube. The only way you will be able to participate in next month's meeting is to be here in person in the planetarium. And if you're not, you'll just have to wait until the following month because you'll be out of luck. Is Alicia here? Yes, bring your binoculars to the planetarium. The planetarium projects the objects so that you can look at them with your binoculars in the planetarium and see them as if you were out in the sky looking at them. So yes, you can bring your binoculars with you, look at the planetarium with your binoculars and see the galaxies and the nebulas, etc., etc. That's right, things you can't see with your naked eye, just like the regular sky. Is Alicia on Zoom?
I don't see her on Zoom.
Okay, so I don't know what she intends to give out as door prizes on Zoom. So what you might want to do is just pick a bunch of people to win door prizes, and they will find out someday what they won.
All right, I'm
As for us,
I'm going to close out the form site now. There are 13 people who signed up and 20 plus people on the session. So if you haven't signed up, go ahead and do it right now.
okay. Anybody who didn't get a ticket?
Oh, stop.
So we have, for the people in here, we have a couple of green laser pointers and a red flashlight. Oh, and a deck of astronomical themed nebula playing cards. So if you're a poker player, we've got the deck for you. And so why don't we start inside while the Zoomy people get ready, and we're about to give somebody a green laser pointer.
And the winning number is 8334. The last numbers is, we got 4884. Who got it? Annie. Gross. Give her a big hand. Yay. What did she get? Annie gets a green laser. Yay. Okay, next, should we do another one here? Or what do you want to do? Spencer, are you ready? Or you want me to go for more here?
Go ahead, get another one. And I'm
Okay.
just getting ready right now.
Okay, we're going to give away another laser pointer.
The number is 8334902. You got one. There you go. Congratulations.
Okay, I'm ready with the Zoom now.
Okay, go ahead.
First one is George Azar.
Thank you. I appreciate it.
See, now, George, if you're here, you get your present right away.
Next time, I promise.
Okay. Then you know what you're going to get. Okay. Go, and you want to go ahead, Spencer, for another
All
one?
right, okay, let me do another one. Hang on a second. Daniel Gillespie.
Awesome. Thank you so much.
And we have no clue what you're getting. Neither does anyone else. Okay. Should we go to our next one here or what? Okay. And the winning number here is 8334907. 907. There you go. Jessica gets it. Okay. And we have one more to give away here. Is that correct? That's right. Okay. So we'll do that right now, Spencer?
Yeah, hang on one second.
Okay.
Let me just. Okay, it's Andy and Victoria Jones.
By the way, the planetarium show that Dave Nakamoto puts on was absolutely fantastic. It was one of the best things we've ever had. He took us. He made the entire area look like the Martian atmosphere at nighttime. It was so cool. And then we went to the southern atmosphere, right? The southern atmosphere.
Southern Milky
and nobody
Way.
could. Yeah, our guys couldn't even figure out. Our most knowledgeable guys couldn't even know where the hell we were, because everything was upside down and backwards. It was so cool. Okay, ready? Here we go. Last number, 8334893. There you go.
Okay, one more on the Zoom.
Yeah, go ahead.
Okay.
You get casino cards. You're lucky to take it to the Vegas with you.
All right, hang on a second.
Okay, we're done. Go ahead, Spencer.
All right. So Eric Shavlov. Eric, are you on?
Yeah, I'm here. Can you
Okay,
hear
all
me?
right. Yep, yep.
All right, way to go.
Cool, thanks.
And don't forget, our star party here is Saturday, this coming Saturday. You can arrive here at 2 o'clock if you have a solar scope during the day. And my understanding is we're going till 10:45. We need to be out of here by. Just don't advertise it. Don't tell anybody.
Yeah, the fact that we're staying an hour late is supposed to be a secret that is not advertised by the observatory. So we get an extra hour. That's right. Shh. Top secret. Keep it to yourself. And now, do you have one more, Spencer?
I don't do. Okay, I need to get one more.
Did
Okay,
you do 4 or did you do 3?
I've done 4.
Okay, then we've done 4 and you've done 4. We're done. And the people on Zoom someday will find out what they won. As for the rest of us, sorry for you guys who didn't win, but if you show up here, you know what you won.